Thank you and good morning. I'm very glad that I can present our work. We is Amélie Trottignon, who told me that she could not join today's talk, but Manuel is here, Manuel Kauers. So if you have any question, don't hesitate to either post the question in the chat or interrupt me. So the title is Quadrant Walk Starting Outside the Quadrant, which might sound a little bit exotic. So I will first try to explain what our motivation was to study this kind of lattice walks, and then present some of the techniques we used to study them. So let's recall a definition. A lattice walk is just a sequence of points of set D. P0 is called the starting point, Pn is the end point. The consecutive differences of these points are the steps, and n is its length. And the typical problem in this setting is you have given 2 points, the starting point and the end point, and 2 subsets, the domain the walks are restricted to, and the step set, the set of admissible steps, and a non-negative integer n. And you're wondering, what is the number of walks in D that start at P and at Q and consist of precisely n steps, all of which are taken from the set S. And how does this number depend on the parameters P and Q and D and S and n? And how does the number of walks grow as n goes to infinity? When the domain is the non-negative quadrant and the set of admissible steps is contained in this set here, then these questions can be approached by studying the following problem. Solve this functional equation for f in the ring of series in T whose coefficients are polynomials in x and y, and decide whether its solution is rational, algebraic, D-finite, or D-algebraic. And in case it is, find an algebraic or a differential equation it satisfies. So it's not difficult to see that this functional equation is a unique solution, and that its solution is the generating function of walks, which start at the point KL in the non-negative quadrant, take its steps from S, and never leave the non-negative quadrant. The systematic study of such functional equations was initiated by Mani Mishna and Mireille Bousquet-Milou in the following paper, Walks with Small Steps in the Quarter Plane. And I think it's justified to say that this article was quite influential. So it was first published in 2008. And I checked yesterday on Google Scholar that it was cited more than 250 times. So a lot of people got attracted, and the classification of the generating functions is now quite well understood. So I don't want to give an overview of this classification. I just want to mention one aspect, namely that there are 2 quantities which can be associated with the functional equation, which capture quite well the nature of the generating function. So to define the first quantity, let's have a look at the step polynomial, which encodes the step set. So y bar and x bar denote y to the -1 and x to the -1 for notational convenience. So it's a Laurent polynomial in y and in x, and assuming that the coefficients of y to the -1 and y and x to the -1 and x are different from 0, we can define 2 b-rational transformations which leave this polynomial invariant. And these transformations generate a group. And this group is the first quantity associated with this functional equation. To define the second quantity, I have to explain what the sign of an element of this group is. It's either 1 or -1, and it's 1 if you can write the element as a word in the generator's find psi of even length, and it's -1 otherwise. And the second quantity is now the so-called orbit sum of the equation. It's the sum of the sign of G times the result of the action of G upon this monomial x to the k plus 1, y to the n plus 1, where KL was the starting point of the lattice walks we are studying. And there's now a theorem which relates these two quantities with the nature of the generating function. And the first part says that the group is finite even only if the generating function is definite. And the second part says the group is finite and the orbit sum is 0 even only the generating function is algebraic. This is quite remarkable, and we were wondering if there are any examples for which the group is finite and the orbit sum is 0, but the generating function is not algebraic. And the answer to this question is, of course, no, because otherwise the theorem would be wrong, but it makes still sense to ask this question, to ask how you can modify the assumptions of the theorem such that it does not hold anymore. So the answer to this question is yes, if we allow the starting point KL to lie outside of the non-negative quadrant. And we investigated a few examples which I want to present now. So the simplest example is to consider this step polynomial, which corresponds to the simple step set. So the associated group is finite, and this is how it looks like. And the orbit sum is this here, which is, as is not difficult to see, equal to 0 when KL is equal to -1, -1. So the functional equation for this choice then looks like this. And we were then wondering about the nature of the solution of this functional equation. Is it definite? Is it algebraic? And before it makes sense to speak of the solution of this functional equation, we have to clarify what we mean by this f0yt and fx0t, because now any solution has to involve terms with negative powers in x and y, so we cannot just set x or y equal to 0. And the most natural interpretation of these functions, the most natural interpretation is probably the following. Here's a picture which explains what we are counting now. We try to count walks which start at the point -1, -1, whose steps are taken from this simple step set with the restriction that we can only cross the x-axis from below, and we can only cross the y-axis from the left. Here's another picture explaining this. The plane divides into 4 parts. We start in the lower left quadrant. And once the quadrant is left, it cannot be re-entered. And once the upper right quadrant is entered, we cannot leave it. For this interpretation, we could solve the functional equation using elementary power series algebra. And this is the expression we found. It looks rather complicated and big, but it's neither big nor complicated. It's not complicated because it just involves rational functions and positive part extractions, negative part extractions, and coefficient extractions. And since rational functions are definite, and the class of definite functions is closed under part extractions, this implies that f is definite. I said the expression is not big, and it's not big because we could use Christoph Kuchan's mathematical package, holonomic functions, to derive a recurrence relation for the coefficient sequence of the length generating function. This is how it looks. And we could compute its asymptotic solutions and observe that the polynomial growth here is either -1 or -3, which is not compatible with algebraicity of f. So this is one counterexample to the theorem under modified assumptions. We also had a look at other interpretations of these functions, these sections. Here's one. Here we start at -1, in the 3 quadrant, and once it's left, we cannot re-enter. And here's another example we had a look at. Here, the plane divides again into a quadrant and a 3 quadrant. We start at -1 in the lower left quadrant, and once it's left, we cannot re-enter. For these two examples, we could show that the generating function is definite, but we could not derive a differential equation for the length generating function. But what we could do was we could guess one and show that under the assumption that the guessed differential equation was correct, the generating function cannot be algebraic. But this time we had to argue differently because the asymptotics turned out to be compatible with algebraicity. And what we did was we showed that f, the length generating function, can be written as the sum of two functions, one of them being algebraic and the other one being transcendental. And by closure properties of algebraic functions, this implies that f cannot be algebraic. So for the rest of the talk, I would like to present some of the arguments. So the question now is, given a differential relation for a function which is of this form, as it's an ordinary differential equation whose coefficients are rational functions, the question is, how can such a differential relation imply the transcendence of the function? And well, the first step is to change your point of view in the following sense. Instead of saying that you have a function f which satisfies the differential equation, you say you have a differential operator which annihilates your function. So changing to this operator point of view is quite useful, because the set of differential operators of this form here has quite nice properties. Well, you can define two operations, an addition, which is obvious, and a multiplication, which reflects the Leibniz rule of differentiation. And with these two operations, it's a non-commutative ring, but not only this, it's also a right Euclidean domain. So you have a notion of division with remainder. So for each two operators u and v being different from 0, the unique operators q and r, the order of r being smaller than the order of v, such that this equation holds. We say that q is the right quotient of u and v, and r is the right remainder of u and v. And we say if r is equal to 0, that v is a right divisor of u, and that u is a left multiple of v. Of course, there's also a notion of greatest common right divisor and least common left multiple. We denote them by GCRD and LCLN of u and v. Okay, so the next step is to check whether our operator L is completely reducible. The class of completely reducible operators is somehow nice because it allows you to decompose your operator into smaller and simpler operators. Here's the definition. So we say an operator is irreducible if it cannot be written as the product of two operators of smaller order. And we say it's completely reducible if you can write it as the least common left multiple of irreducible operators, L1 up to Ln. And the reason why this is very helpful in our setting is because the solution space of L, it's a vector space over Q. And if you know that L is the least common left multiple of these irreducible operators, and if you know that this representation is minimal in the sense that L cannot be written as a least common left multiple of a proper subset, then the solution space of L is the direct sum of the solution spaces of the Li. And the Li's being irreducible now allows to investigate their solution spaces quite simple. So the next step is to check which of the Li's only have algebraic solutions. And for this, it's helpful to know that if an operator is irreducible, then it either has only algebraic solutions or the only algebraic solution is 0. Now, how can we show that it has only algebraic solutions? So what we did was we computed the first terms of a series solution of Li and then tried to guess a minimal polynomial for it. And if you can find one, you can derive an annihilating operator for its solutions, for its roots. And the next step is to compute the greatest common right divisor of this operator n and Li and check if it's equal to 1 or different from 1. If it's different from 1, then the irreducibility of Li implies that Li is a right divisor of M. And this implies that the solutions of Li are all solutions of M. And since M does only have algebraic solutions, this implies that Li does only have algebraic solutions. So, of course, this does not always work. For instance, it can happen that the minimal polynomial is so big that you cannot compute sufficiently many initial terms of the series solution. And it can also happen that the operator does not have any non-trivial algebraic solutions. So the next question is, how can we show that the solutions are different from zero transcendental? And yeah, one way of doing so is to inspect the generalized series solutions of the operator. These are series solutions of the following form. And it's known that if there is a series solution which involves a non-trivial exponential part or a non-trivial logarithmic part, that the series cannot be algebraic then. So all the non-zero series solutions of the operator are then transcendental. And yeah, having now checked which of the irreducible operators in the representation of our operator L as the least common left multiple of L1 up to Ln only have algebraic solutions, we know that any solution F can be written as a sum of solutions F1 up to Fn, where Fi is a solution of Li, where let's assume the first k minus 1 are algebraic and the remaining ones are transcendental. Then it remains to show that the transcendental parts don't sum up to something algebraic. And how can this be checked? Well, if F were algebraic, then so would be M applied to F for any operator N, in particular for this least common left multiple of the Li's minus Lk. And so the result of applying this operator to F is different from 0 by minimality of our operator L. And we can now construct from this operator and from the operator L another operator P, which is smaller and which annihilates M applied to Fk. And if we can show that P does not have any non-zero algebraic solutions, this is a proof that F is transcendental. So to summarize this, if you want to show that a function is not algebraic and you know it's definite, then you should make use of the fact that it's annihilated by a differential operator. So differential operators are useful. Then we check if the operator is complete reducible. So if you can write it as the least common left multiple of irreducible operators, and check for each operator in this representation whether its solutions are algebraic or transcendent. And then check whether the sum of the transcendental parts of your solution of the operator don't sum up to something algebraic. Okay, and here are a few references. So the first reference is our paper. The second is my PhD thesis, which I finished last November. So here you find more details. And the other references are the software that we used. And there's Manuel Kauer's guessing handbook, which we used for guessing the differential operators. There's a Mathematica package, also written by Manuel Kauers, for computing asymptotic expansions of solutions of recurrence relations. There is Christoph Kutschan's Mathematica package, holonomic functions, which we heavily used. And we also used Maple for computing the factorizations of our operators. Okay, and that's it.
Okay, thank you, Manfred, for the talk. Let us thank the speaker. There is time for questions. Let me quickly check the chat. Nothing in the chat so far. If there are any questions from the audience, it's probably easier if you unmute yourself, so please do so and ask the question. I have a technical question. Maybe I missed it when you spoke. Is there if you have an operator that you suspect is a product of smaller degree operators, you're telling me there's an effective procedure to factorize it, or?
Yeah. And there's even an implementation in Maple. It's, I think, D factor LCLM. You just input your operator, and if it does not take too much computation time, then you get as output those irreducible operators, or some operators whose least common left multiple is your operator. And then you also have to check whether these operators are irreducible. And for this, you can use another command, D factor.
Right.
But it is very likely that your operator is too big, and then you have to somehow work around. Yeah, we have to do this.
And this is, of course, only for one-dimensional, so for one variable operators, right? Not
right.
Multivariable.
Yeah.
Other questions from other members of the audience? If not, let us thank the speaker again.